So I think this needs a little bit of explanation. Welcome to TBD session. It is to be TBD, I think. So the thing is that this presentation was supposed to be done by one of our colleagues called Duncan, and he had to take care of some family matters, so he left. So we are Plan B. Okay, so what you're going to see here is actually essentially done after the party last night. So we in fact have a few minions at the back. We're actually cranking out the last pieces of the slides here as we speak. But thanks to the vague title of this presentation, we felt like we can fit in lots of interesting stuff. So I have Markus with me, who's going to help me with the thing here. But instead, what we decided, instead of talking about various reactive architectures, we're going to focus on only one. And we're going to take it to the next level a little bit, because since we are both working for Typesafe, we had an opportunity to implement reactive application in the wild out there. So we're going to essentially highlight few patterns that we found very interesting and useful. While we do this, I will really encourage you to guys to ask me a lot of questions. Okay, if you don't, as I said, we probably have 20 slides here. We'll be done very quickly. So back to minions.
Okay, so basically if we're not doing client work, like on the side, we're also doing some internal work, and right now we are also building a learning platform, and we thought about that's like a really good use case for a distributed system, right? So like a learning platform with a massive amount of users, so millions of users who are doing like all the time like writes and always updating their progress. So we thought about to talk a little bit about that. And also because we didn't have anything prepared before. So who doesn't know like these properties? Who doesn't know anything about the Reactive Manifesto? Okay, perfect.
You, sir, are out of here. I'm kidding.
That's good. It's an intermediate talk, so that's what's the expectation. So I will not go through all the properties again. But we will show now, basically based on 4 problems, based on 4 challenges you can face if you develop a distributed system, how you tackle that. And we will show basically how to create a responsive, resilient, and elastic distributed system. So our learning platform looks like that. We have basically a web frontier, right? So a bunch of play instances on the front. And then on the back end, we have a bunch of Akka services, right? So very typically, therefore, we can basically scale down different kind of services in a different manner, right? And on the back end, which is where we're using Akka, we are also using Akka persistence. So if we persist certain actors, we are saving them, we are storing them in a Cassandra database, right? In an event log journal fashion. And also, because we are using event sourcing, Spark fits really nicely into it, because then Spark can do like very heavy analytics based on the Cassandra database. So that's like really rough architecture. Later on, we also will see a slide what kind of technologies we are using. All right. So
some of these patterns going to have we're going to identify the problem. We're going to say why we have used a pattern. Then we're going to say what Akka essentially provides. So most of the stuff is going to be Akka. And we're going to talk about that in details, and then we're going to look at some of the code examples. That's going to be essentially how we go. We have 4 or 5 of them. Depending upon the time, we will see how far we can go. So the first problem is splitting an application. This usually happens when you start an application and based on multiple Akka services and play applications we're building, we got into a point where our application turned to be really big. Okay? It looked like this in deployment. So we had this monolithic app which had those circles, those Scala circles supposed to represent services, components. Think of them as a components, okay? So we had these components. So way we had deployed in a cluster is that take the entire application and made replicated deployment in all the nodes. Okay? The biggest problem with this approach was, I'm going to start with the developer productivity. So every time a Play developer made some changes, Play automatically reloaded the application. That meant reloading the entire actor system over and over again. It obviously reduces the developer productivity. That was first concern, the first problem that we encountered. We thought that will not scale very well. Second aspect of this kind of monolithic application was, now if you look at this, in our application, when Markus was talking about the high-level architecture, our play was essentially a REST gateway, right? It will take HTTP requests and give it to all our Akka services. So if we think those green circles are play application, the red and blue ones were something which we want to scale, okay, scale out. That means we are getting into a situation where I want to take parts of my application and deploy it into more nodes. Okay, so we wanted to achieve something like this. Okay, if I have in this case, what I'm showing here, this diagram is showing is that I have a cluster of 5 nodes where we said, okay, play is not doing much, we're going to put it on 2 nodes there, whereas all the services that we have on the back end, we want to scale it separately. It gives you that flexibility, right? One way we are trying to achieve here is some sort of a microservice-based architecture. Now, when you get into this kind of model, which we really appreciate, because now look at the developer productivity side. When I update my play application, I don't have to restart all the VMs that's running here. The downside of this, or challenge of this problem, is to figure out how can my front end now talk to all these backend services? How should I integrate my microservices? So my challenge was, first challenge is location transparency, right? If I go back to this, as a play application up there, I don't know where is my red service running in a cluster, okay? Today it's running in here, I could add more nodes to my cluster depending on the demand, and that service could be running somewhere else, right? So one of the challenge was to figure out something that gives us a location transparency, where I can say, invoke the red service for me. I don't care where it's running. Second aspect of was the publish-subscribe model is kind of very interesting to us, because if you are doing microservice-based architectures, there's 2 types of integration you can do. Something is called orchestration versus choreography. These are the 2 alternatives you have. Okay, the orchestration is the easiest way to go about, where you have an object, a service, which knows how exactly you should send your requests to whom. Okay, some sort of God object, which means that it increases coupling in your system. The one that I personally prefer is choreography, where you say, okay, I have something to do, and you put that event somewhere you publish that event. And whoever is interested, in this case, whoever service can respond to that event, picks up the event and does some work. And finally, something that allows us to dynamically add and remove node based on the requirements. All this got satisfied. There is a component in Akka called distributed pub sub. Okay, it's an external contribution component in Akka. If you use that, we get into something interesting here. If you use that component, what this component does is that on every node, it starts something called mediator. Okay, it's an actor, and this box here, mediator component provided by that Akka, talks to each other via gossip protocol, and kind of forms this eventual model of where everything is running. Okay, now so another level of essentially an indirection. But the benefit of this indirection is now each of these components can easily talk to other services running in the backend. Please ask me questions so that I can get a feel. Thank you. Yeah.
Sorry, what was the protocol that they used to
gossip protocol. It's influenced by what React does. We got inspiration from there. Any other questions? Yes. Locations of the node. Let me show you the code again, then we'll probably make some sense. Yes. It's essentially gathering information where all my services are running. Any other question? Yes.
This might be obvious to someone else, but the mediators, once they're communicating, they can propagate the information about what node is where.
Yeah.
Don't you have to get all the mediators in connection with each other first?
No, but since all these nodes are automatically part of an Akka cluster, that information gets shared. The line corresponds here that they already know each other. These nodes already established that connection. Any other? Yes. Sorry.
When you're rolling out the next live deployment, how do you keep it so that you bring certain nodes down, put in the next version, and promote.
It's more of how you manage microservices, though, right? You have to deal with multiple versions of that reality. So given a given point of time, we're going to have multiple versions of this red service running. Let's hold on to let's move on quick, okay? So this is the idea. This provides this abstraction. So we can get into that model of actually the benefit of choreography. So if I wanted to look at the code here, I am assuming that almost all of you know how actor model works. This is not at all an introductory session, okay? If you have any actor-related question, please ask me. But imagine this is part of being in some actor system code. If I'm in a front-end component, okay? In that case, what I'm going to do, obviously this line I'm going to execute. What I'm doing here is that I'm taking a distributed PubSub extension. Akka extension essentially you can think of as a plugin where you can add features to actor system. In this case, I'm using an PubSub extension to get a reference to mediator. This is my actor ref, that box inbox. But once I have that, if I want to invoke some service, obviously this is related to a learning platform. In this case, we are saying, hey, I want to send a create course message to actor which is running in this relative path. It's very important to note, I don't have any machine address here or IP address here. Okay? And here, this has an alternative parameter, which is very useful if you're running in dev mode, where I'm saying local affinity. So it's going to look at do I have this service running in my local JVM first? So here I'm using an ask pattern, so I'm getting a reference to a future. On the other hand, on the back end, what's happening, obviously, we're doing the same thing. I'm initiating a mediator. And once a mediator is done, this is where I'm registering my services. One of the good way of designing microservices is obviously doing the domain-driven design aggregates, right? So this is my course aggregate, which allows you to create new courses in the system. Once I have this actor ref, then I'm saying, mediator, please register my service. And similarly, we are doing for the other service here.
All right, I think it's my turn again. So that's already really cool, right? We already have Akka clustering in place. But like this kind of thing mainly only works with, the clicker, mainly only works if you have actors which are maybe getting initialized with a state, but the state is not changing, right? So what about like actors which have a state where the change periodically changes, right? So let's say in our learning platform we have a user actor, and the user actor starts specific online trainings, he's finishing certain exercises, and we always want to keep track of his status, of his progress. So then basically what we need to do is we need to keep, let's say, all the user actors in one particular node, right? Why is that? Because let's say I create a user actor on one node, on node A, then all the messages which are related to this user actor instance also need to be routed to this node A, right? If like a message is routed to node B, let's say get user message, and this user is not available on this node B, then it says user not found, but actually the user exists on node A. So basically we need to put all our users on one node, which is fine. Like with Akka clustering, we can have a specific role, so we can say, okay, all the users should go to this node. Fine. But the problem is here distributed state. So what happens? We have millions of users, right? Unfortunately, nowadays our machines do not have infinite RAM, so we can't store like all the users just on one node. But we still want to be responsive, right? We still want to keep like all the state in memory. We don't want to save that to a database, so that we like, really responsive. So what we need to do is we need to distribute the state by still keeping in mind basically where the user actually is located. So whenever like a message is sent to this certain user, it always goes to the certain node where the user sits. right? That's actually a tough problem to solve. So we used Akka cluster sharding for that. Right? So Akka cluster sharding partitions actors across the entire cluster. Right? Also, a really nice thing is it's completely location transparent. So, for instance, the front-end service, if you send a message to this user actor, the front-end doesn't need to know where the user actor actually sits on the back-end. Right? It's completely location transparent from the caller point of view. And basically Akka cluster sharding takes care of that, and we will see some code how it actually works. Also, Akka cluster sharding automatically rebalances all the user actors in our case. Right? So let's imagine on 13th of April we are starting a new training. It's called the Principles of Reactive Programming, right, by Martin Odersky, Eric Meyer, and Roland Kuhn, and we already know beforehand that we get like a huge amount of traffic. So beforehand we will, let's say, create like 100 new nodes. Right? So now what we want to do is that we rebalance all our user actors also to the other nodes. Right? And also Akka cluster sharding automatically takes care of that, because then all the requests which are coming in, they're not going like to the older nodes, they're going to all the nodes, so it's nicely distributed. All right, so Akka sharding is kind of, say, not a super easy concept, I would say, therefore, like additional slide here. So how does it work? So first, on every node which participates in Akka cluster sharding, we need to create a so-called shard region. Right? So on each backend node, also on each front-end node, we need to create a shard region. And the shard region has a responsibility to route the message to the specific user actor. So the shard region knows basically where my user actor sits, right? So if like, I know I get a request and it's routed to node A, there's a shard region, and the user actor actually sits on node B, then the shard region on node A reroutes that to node B. Make sense?
There's one thing I'd like to highlight here. So this is one of the biggest benefit of actor programming, right? You can take actor and represent your domain objects in your application. So each of these red circles here represents user. And there could be one Nilanjan or one Markus in your system, right? So we are essentially, so each of this, even though they are colored red, are unique by its own. They have their own identity with state.
Right, but from the front-end point of view, it's completely location transparent. And also, the shard region basically takes care and sends basically the message to the Nilanjan actor or to the Markus actor. So now we also have, so that's fine, right? So the shard region basically stores the information where the user actors actually sit. But what happens if I start up now like new nodes? Right, so we already created like a couple of users. Now I start up new nodes. So with this node, I also start up a new shard region. That's basically just an actor ref. We will see that shortly in the code. So now this new node, this new shard region, is not aware of all these, where all the user actors have been created, right? So how do I do that? That's where the sharding coordinator comes in place. So basically the sharding coordinator is a cluster singleton pattern. It doesn't sit just like somewhere outside of the cluster. It basically sits on the oldest member node of the cluster, and the sharding coordinator basically stores all the information in a persistent way, with also Akka persistence underneath, where all the basically user actors are stored. Right? One question?
Is the same sharding coordinator also aware so that if one of the regions goes down and you know, so that it doesn't lose those users, you know, will you have lost those users in that other region, or will the coordinator know, like, okay, go ahead and rebalance and stuff, or create a new one?
Yeah, so good question. So if this node goes down, then the user actors on this node are lost. Right? We have no persistent yet. We will tackle that in the next problem. So that also will come into place. We also will basically lose the information for this particular shard region, right? But that's not really much a problem. We can start up a new node, if we persisted, let's say, our user actors, it's fine to lose the information where, like, let's say, other user actors are sitting, because we have the sharding coordinator, and he's persisting basically all this information. So what happens if a new node comes up, and let's say I get like the first request of a new user actor, the shard region is not aware of that, is it will ask the shard coordinator. And the shard coordinator will send a message back and say, okay, here, this user actor sits on this node, please reroute that. Right? And then the shard region stores this information, and he don't need to basically goes to the sharding coordinator again anymore. Right? Yeah?
Are the actors also replicated?
Which actor? The shard coordinator?
Within each individual user actor, are they replicated?
Oh, but that's the point though. We cannot replicate. Like I said, there could be only one Nilanjan. The problem is if I have two Nilanjan running in cluster, then they could have different states.
Yeah.
And that could bring up a different set of challenges.
I mean, also here, so you're using this kind of pattern if, like, distribute basically your users across the cluster if all your users doesn't fit into one memory in one machine, right? So if you now replicate it, like, that doesn't work, right? All right, so we're almost there. So now we have like this kind of circle, right? So we have here our user actors, and we have this kind of circle, this black one, and that are so-called shards, right? So shard are basically just grouping a set of user actors in our case. If it comes to Akka cluster sharding, actually the actors within the shard, they're called entries. And that's just because of performance reasons, right? Because the shard region, but also the sharding coordinator saves information where not actually the users are sitting, but the shards, right? So they're just groups, and therefore it's just more performant. The shard region and sharding coordinator doesn't need to save so much information. All right. So let's look into some code. So first off, we said, like for each node which participates in Akka cluster sharding, we need to create a shard region, right? So on the backend side, that's basically where we store all our user actors. We write just this code. With this code, basically we create a shard region. So we say cluster sharding, give it an actor system, and say .start, and then we need to specify certain kind of parameters. So the first one is basically the entry type name. So in our case, we want to shard a set of users, so we just give it a name of users. Right? The second is the entry props. So entry is basically the user actor, right? So because we want to, we are dealing with users, we are specifying the props of the user here. And then we also need to specify an ID extractor and a shard resolver. So what the heck is that? Basically, these are methods to identify where this actual user actor sits on what kind of node, right? So we have a shard resolver, which basically extracts the information where basically the shard region, right, needs to route the message to what kind of node. And the ID extractor, in a nutshell, has the information of the identifier of the actual user instance, right? So if I'm at the play front end, we will see that, like on the next slide, I do not have the actual user actor ID reference of the certain user actor, right? Of the certain instance of the user actor, where I have an ID and things like that. It's completely location transparent. I'm only sending messages over a shard region, so therefore the shard region need to know basically to what kind of real user actor instance I need to send that. And therefore we have this ID extractor, which contains basically the user actor identifier, in our case it's an email, and the payload. So the payload is basically the message we actually want to send.
So another way to think about it, in your slide when Markus was showing the shard region, so you all remember from your application point of view, next time you want to send some message to any of this user, you'll always go via shard region. That's why shard region needs those ID resolver and shard resolver to kind of figure it out, that where should I go to find that user actor so that I can forward that message.
All right, and now on the front end, it's super easy. we're also creating a shard region, right, for each node. So basically in the global, like in the play global, on the backend side, we are just doing it in the main. I will come to your question in a minute. And we are creating also the shard region. So here's now an important fact: we are not specifying the entry props, right? Because if we are not specifying the entry props, so we're saying here none, then we are creating a shard region in proxy mode only. What is that? So proxy mode only basically participates in Akka cluster sharding, but never stores any user actors in our case. So it only has a responsibility to route the message to the backend server, but never basically creates actors actually in the system. And we don't want to create any actors on the front end, right? They all should be on the backend. Okay, so you had a question?
Yeah, how would you handle dynamically adding a shard? Like in the previous example, you showed a fixed number of shards you saw.
So there is a rebalancing feature in Akka sharding, which kicks in, and there are many ways. There is bells and whistles knobs that you can actually have this shard resolver strategy, so you can plug in your own strategy also.
Yeah. And now on the front end, it's super easy, right? So we have the shard region, which is just an actor ref, right? And underneath, basically, the shard region knows where to route these messages to what kind of user actor, and we are just sending a message, right? So here in this case, we are sending a user message, and basically we need to wrap this user message, our get user message, in a case class to also basically send the ID. That's like related to this ID extractor. So basically that the shard region knows what is actually the ID, the identifier of this user actor. So that's our cluster sharding. Okay, so now the next state, we already talked about that. What happens if a cluster goes down, right? Then all my users are gone. Damn. I mean, so now we have like a really scalable learning platform, right? Which can handle millions of users. But let's say I'm a user, I'm super passionate, I did like 10 online trainings, and then on the next day, all my progress is gone, right? I mean, then we have like a really scalable system, but no one would use our system because it's not reliable. So therefore, like in some certain cases, we need to persist actually the state. So what we want to do is, every time we are changing the state of our user, every time we are doing kind of a write, we want to persist that to kind of like database, and then if a node goes down and let's say another node comes up, then we want to restore our user actors and also restore the state, right? So that's the idea. And for that, we used Akka persistence. So Akka persistence stores basically the state, in our case a user state, in a journal database, in a kind of event log, right? There are different kind of community plugins out there. You can use different kind of databases. We use Cassandra. You can use Kafka, MongoDB, and also others. And here the important point is it doesn't store like, let's say, just the last state of the user. It stores the events, right? So it's event sourcing, so it stores each event. So like if I create a user, it stores this event to this journal database. If I do kind of like an update user, it stores also this event to this journal, right? So now the nice thing, because it's event sourcing, I can travel back in time, right? Or for instance, so like on a chess game, I could do like undo buttons, right? And then easily like restore my old state because I have all the messages still in the database. Or what we also can do is, now with Spark, we can do like really nice analytics based on all the events which have been stored in the Cassandra database. So now if we want to restore the state, what we do is a new node comes up, we are starting up our actors, our user actors, and then we are replaying all the events, of course in the correct order, for this user actor, for this particular user actor, and therefore at the end, after all the events have been replayed, we are back and have restored our state. All right, so let's see some code. So the benefits of Akka persistence is like the reads are super fast, right? So if you do a read, it's just a normal read, like to your Akka actor. You just check out like your mutable var and give it away, right? There's no access to the database. Even we have a database underneath. The database is just for persistence reasons, right? So only like in terms of writes, you're basically talking with a database, and also the writes are super fast because it's a journal, right? We don't need to do like any joins kind of things. We're just like putting off all, or like writing all the events into this event log. All right, so to basically change a normal actor to a persistent actor, or basically to enable Akka persistent, you're just not extending from actor, but from persistent actor. First thing, then you need to override a persistent ID, and the persistence ID basically tells the journey database and what kind of, let's say, table this needs to be solved. So that's the identifier for the journey DB. And then, instead of basically implementing the receive block, you need to implement a receive command block, right? So we still have here our messages, as you know it. So for instance, we are creating a user, and whenever we want to, basically we have a message or an event which we want to persist, right? Kind of like a writing event, then we are calling the persist method, which comes with our persistent actor. So the persist method basically persists the actual message which we are specifying here. In our case, it's the event user created in our Cassandra journal, right? And if the event has been persisted, then we are going into this block, and we are fine. We know everything worked, and we can update our state in our user actor memory, right? So we're updating basically the var user. And in this case, the last piece is that we're sending back a message to the front end and saying, okay, user has been created.
Is there some equivalent to like context become for receive command? Like, can you still do that kind of by a state machine?
Yeah, completely. Yeah. All right, and now the last piece is like recovering the events, right? Restoring the state. So here we can basically implement another block, receive recover, which kicks in every time we are starting our actor, right? Every time we are starting our actor, we want to restore the state, and now we can do pattern match on our events, which we have stored in our journey database. And when the user actor starts, we are retrieving all the messages from our journal in the correct order. That's guaranteed, and in our case we are just calling the onUser created method to basically do all the updates on our user mutable variable. All right, so that's Akka persistence.
Question about that last point.
Yeah.
Does this mean you have a whole bunch of different events, and so potentially of different types, and you receive them in order, and then that's how you reconstruct your state?
Yes. So I mean, if you have like different kind of types and you need to do pattern match on these different cases, yeah, that's possible. And also if you have like 1,000 writes or 1 million writes, yeah, like during the replaying, you would replay, or you would basically react on 1 million messages. What you also can do is you can create snapshots. So you could, for instance, say like after each 100 basically messages, I take a snapshot, and this snapshot is saved in the journal database, and then like during this receive recover state, basically it first sends you the snapshot, and then afterwards the messages which have come afterwards.
But you also give you are guaranteed in order.
Yes. Yes. So like how do you snapshot your things? That's up to you. Yeah. So any other questions? Yep.
An implementation detail, where do you keep the database? Is it on the same node, same disks, or is it a server?
If you do it right, you should put it in a different node. Yeah, a node which should not go down. I'll try to, yeah.
And also in a distributed fashion, right? So it shouldn't be just like one journal, because like if this is out, of course, like the data is still stored. Maybe the disk is corrupt, then you can't restore it, but it needs to be in a distributed fashion. Yep.
What about the persistent database where network spoke? The new event comes in, will it persist or store the memory when the database comes come back and flash to it? How do you handle it?
Can you repeat the question? Sorry.
Okay, for example, Cassandra is offline. New event comes in.
Yeah. So if Cassandra is offline and new event comes in, so I think I don't know whether Akka persists in. Patrick, do you have?
I don't really get the question.
So he's saying that the Cassandra is down.
Yeah, then you will receive a persistent failure message back.
Yeah.
So that is overall not. No, exactly. That is lost. So then you must handle that.
Yeah, but on the other side, you can stash it if you want to.
Yeah.
Because it looks like the plugin's going to give you a notification that I'm down.
But that's the same. I mean, if you just use like a normal Cassandra database or MySQL database without Akka persistence, if like all the entire databases are down, then you also get an exception, right? So it's the same case basically.
Let's get his question. Yeah.
So I'm wondering if all of your user actors are always in memory, or if they expire.
That's a great question. One of the biggest. You want to take it? The passivation.
Take it.
One of the thing about that the Akka sharding has is passivation mode. So you can. So one naive way to do it, shortcut way to do it, is that you can set a receive timeout for your actor, and when you get the receive timeout event, you can say Passivate. So essentially, that actor will be garbage collected. Since you are saving the state in the journal, when a request comes in for that particular user, Shard will create the new actor, journal will replay the events, you get the state. Yes, can we, let's hold on, let's do the next one. This is a pretty hard thing, and I want you guys to hear it. Actually, I'm very excited to talk. So next problem we're going to look at is a replicated cache. Okay, this is, so if one of the next thing that we encountered after we started doing this refactoring in our application is this guy out here. Okay, this guy is essentially, our cache was a cluster singleton. That means given mode for all the cluster, there will be only one actor instance running. Cluster singleton is generally not a good way to do things. We should avoid it. But the biggest problem here is that obviously this is becoming a huge bottleneck for us. These are the course information, level information that we want to render the web pages as soon as possible. Well, if not this, then do what? We do put this cache in both the nodes. Then if we put the cache in both the nodes, like there was a question like that, we replicate this cache, then the obvious problem comes in. Then wait a minute, what if somebody adds something in this node and removes this node, what's happened? So for whenever we had this replicated data and we talked about conflicts, most of the time we got this hand-wavy answer so far, saying, oh, it's just an application problem, you have to design it whenever that concurrent edit happens, you have to figure it out. So Jonas Bonnier mentioned this already, so there is a thing called CRDT. Okay? CRDT is a very, very interesting, because this tells you that where things are evolving, right? This is kind of a glimpse of a future here. It says that, hey, we have figured out a way where you can you can replicate your data and it's guaranteed to be conflict-free. That means even if there is a concurrent edits happening, this replicated type, based on some constraints for some defined types, it will automatically figure out and continue to move forward. So replicated, the CRDT, conflict-free replicated data type, is specially designed for achieve strong eventual consistency. It's not going to happen immediately, but eventually it's guaranteed to be consistent. If you want to, we obviously don't have time to go through the details. This is an excellent presentation. Highly, highly recommend. Again, Sunday afternoon, you have nothing to do. This is the thing you should look at. So what does that means to us? CRDT has two options. I will check the time quickly, okay. CRDT has two types, okay. This type is called, let me check what minions have put in here, convergent replicated data type. What that means is, if I have this edits happening here, then what this mode will do is that this will transfer the delta of state changes. Okay, so let's take a quick example here. What we're trying to do here is that we are trying to figure out the max value. Okay, so somebody has updated X here as 1, and in the other node, think of this thing as the 3 different nodes. Okay, we replicate it in 3 different nodes here. So in one node X is 2, X is 4, sorry, another node is 1. then in CRDT, this deltas will get translated, and based on if you're performing a max operation, eventually all the nodes will end up with 4. Okay, and it's guaranteed to do that. On the other hand, there is another alternative of CRDT. This is based on passing operations around. Instead of delta changes, you pass the operation that will trigger the change. So far, we don't have this implementation. I know there is a framework called Event where people are trying to do that. This is obviously a very research and exploration area. But the good news is that we actually have an implementation of CVRDT, convergent data type, in Akka. That's called Akka data replication. What this allows us to do is that this framework implements CRDT for Akka cluster application. It allows us to have replicated in-memory data store with low latency because it's going to be in memory. And it has very rich types here. When you think CRDT is actually a type, like int is a type, string is a type, this is a type here. And some of the types are like gset. That means this set you can only add things to that. OR set is observe remove state. Here in this set you can add and remove elements. There are stuff like that. PN counter, for an example, positive and negative, okay? All these types, if we use, it will be conflict-free, that's guaranteed. This gives us an interesting opportunity because using CRDT, now we can model our cache. Doesn't matter what happens in these nodes and how this cache components gets updated, we know or strongly guaranteed that this to cache will be consistent. Let's see how that looks in a code, then we'll take some questions on this. Again, replication, this is like a very common theme in Akka that you create extensions to again add behavior. In this case, we are using an extension called data replication. What this extension allows you to do is that allows you to get access to this replicator. This is a guy who will do this stuff for us. This thing. This arrows passing deltas around. And finally, let's say if I want to get something from my cache, I would say, hey, replicator, get value for this key. Then you have a bunch of preferences here. You could say, try to read the local copy that we have in this node. And this is context information you can pass. For an example, I could have implemented this using the tail pattern and send the sender as a third parameter here. That's on the front-end side where we're actually reading the cache. On the back-end side, what's happening, imagine this code being part of the event handler in his persistent actor code. Whenever an user actor or course actor gets modified, on the event handling block, we will put this stuff. Hey, our course got updated, so let's update the replicator. This is my replicator running on some back-end node. Saying, hey, update my replicator for this cache key. If I'm doing for the first time, my set, the type I'm using here is a G set. Because code, so in this application, we're assuming codes will always get added, will never get removed. If I'm doing for the first time, it's empty. Otherwise, call this callback function. That's it. So we have a few minutes for questions. Yes?
So for stuff like active persistence, I haven't actually seen the data replication before, but I know persistence is still listed as experimental. Is that expected to come out of that stage in 2.4? And also, how has it been working for you in terms of reliability? How often do you have this change?
So Akka persistence most probably will not, will still stay experimental in Akka 2.4. So if not, you can ask Patrick, but he said it's right. But it's still used like in many production systems, so it will definitely not go away. I also would consider it as mature. It could be the case that the API will change, but that's about it. Akka data replication is even a little bit more experimental, yeah, it definitely works, and also like it's used in production environments already.
Yes.
I can add one thing. For Akka persistence, the right side is very stable and working fine. What we want to do is add additional capabilities for replaying. on the query side, probably based on Akka streams. So that's something we want to add, and therefore we probably not make it into 2.4.
Oh, that's Patrick from Akka team, by the way. Any other question?
Is there a possibility of like a network split where one node can talk to another, so maybe the same user can be created?
I thought Jonas said network is reliable. I'm kidding. Yes, absolutely.
Handle that if you had two instances of a user and then and rejoin them.
That's a great question. Yes, if we get into a split bin scenario, then yes, we can potentially end up with two users. Then one of the things, obviously, you have to think about in this scenarios that you disable the auto down feature, and I'm assuming your DevOps will kick in and do something. I mean, I'm giving you a hand wavy answer because it very much depends on what kind of application you're building, but it's totally possible. Yes.
Instead of distributed PubSub, couldn't you have used a cluster array router to communicate between the front end and the back end?
That's a great question. So the cluster array for others, cluster array router is the distributed PubSub is pretty low level. In fact, cluster array router, I think, and some of this abstraction builds on top of distributed PubSub. This was like a very underlying. Cluster array router allows you to obviously have routes running in a cluster. One of the reasons I didn't, I'm still debating, I might refactor this code to cluster array router, is because I had many types of services. So if I went with a cluster array router, I would end up with many types of cluster array router. And then there is maybe a potential opportunity I left out so that we can do essentially choreography later on in the integration there. Yes.
Question, but why did you decide with Cassandra as your persistence backend rather than Kafka or something?
Good question, because Cassandra is mostly used as a plugin for Akka persistence. Both are performing really well. So when we started, that was also like a couple of months ago. Like Kafka was not as mature as it is right now, but Kafka is also really good choice. Okay, I would say last question.
What strategy would you use if you have to start looking up user actors by some other property besides their ID?
Can you give me?
Maybe I'm misunderstanding, but if essentially your database is in actors,
Yeah.
you need to look up by some other criterion, like social security number or some other.
Okay.
If you cycle through the whole thing, what would you access the underlying database directly?
Yeah, I would not say this is a replacement of database. So maybe that's not the right way to look at sharding here. Essentially, we essentially wanted to have maybe a user table in memory. So that we can have this faster. Actors are cheap. I mean, lots of financial institutes are doing that. I mean, millions of them clustered in the area. So if I need the query requirements, it's very critical. Maybe this is not a good model then. Yes, last one.
Is there a way to send a message to all of the actors?
All the actors in the system. It depends. I mean, yeah, there is you can wrap messages around broadcast, and there is a broadcast routers. Yeah. Okay. Yes.
So I just wanted to add one thing regarding the query.
Yes, query. Yes.
Yeah, that if you want to have a query model, you replay that's the kind of what we're talking about. Like replay your event into a model that fits your query, because then it's definitely not for query.
Yeah.
It's just the right thing.
Yeah. If you were doing CQRs, then you can back each of this persistent actor. Markus mentioned this in views.
Yeah.
And you can have persistent views.
Look at that.
To have separate reads there.
Yeah. Okay, perfect.
All right, catch us if you guys have any question here. Okay, thank you
very much.